Okay, welcome back to Parametric Fill. Today we're looking at this project, RB Pharma Office by Galant I.D. LDA. This is a beautiful interior space. I mean, I would love to just hang out here on a daily basis. I mean, maybe I need to be a pharmacist in Portugal. I mean, it'd be worth it just to, hang out here. There's a lot of aspects of this design that I think are brilliant. There's also a lot going on, which is difficult to manage, I think, in a project like this when there's so many different design motifs going on. But I think they pulled it off pretty well. The color palette is beautiful. Obviously, I mean, they really did a good job on that. And there's a lot of interesting features, build features in this design. But if you look, a few of the things that are really interesting for us when we're looking at parametric design is this kind of wood installation on this feature wall. That's a really interesting design with the integrated bench. And it's interesting because it kind of it sort of gives this organic feeling because you can see the randomness. You can see that there's no consistency in the spacing and also the lighting. It really gives that kind of an organic feel, and it just goes to show that like the organic design doesn't always have to be like some like crazy flowy design. It can be something more rigid, but as long as you incorporate some amount of randomness into the design, it kind of feels a little bit more comfortable, I think. So that's the project that we're going to be, this is the part of the project that we're going to be focused on today. But let's look at a few of the other designs that are going on here. I want to show you, they put a tree in the bookshelf, which is, there's a few trees in the bookshelf, which is kind of interesting. I don't know if I like it. I kind of like it, but it's interesting. But we can also see this, this organic motif in, where's that other, you can see them using a similar kind of design in this wall here. They have the lighting, the strip lighting, but you can see they've integrated that kind of randomness in here, which I think is doing the same effect. When you integrate some amount of randomness into the design, it kind of loosens it up and makes it feel more natural, I think. But it's sort of like a modern interpretation of a natural environment, because obviously everything is 90-degree angles, straight edges. So it's always kind of an interesting, oh, here's another picture of it. Really interesting design that they're working with here. But obviously a lot of different, there's so many things going on here. I don't know if it's too much, but it seems to work pretty well. So it would be fun to check this place out in person. So anyways, let's take a look at this feature wall. Well, I don't know if it's a feature wall. There's a lot of features going on here, but this wall in particular, this is a project that could benefit from a parametric tool like Grasshopper. As you can see, it's like an array, because every single piece is the same, and we're kind of arraying it, except the spacing is not consistent. The spacing is random, and then we're going to punch some holes into the design basically to create our benches. So that's the fundamentals of how this is working. Now, a few of the things that we want to be thinking about though is, how do we create spacing that's not too large, not too small, but mostly how do we create this array so that the objects don't overlap, right? Because we have spacing here that goes down to like 10 millimeters, it looks like. We have some spacing that goes up to like 400 millimeters. And how do we create something like that so that these objects don't overlap? Well, let's take a look at the Grasshopper script, okay? So let's head in here. This is one of the renderings that we ended up with. And this is what the model looks like. The script is it's bigger than I thought it was going to be. It got a little bit out of hand when I got really into the parameters, and I wanted to be really strict about the final, parameters of this design. And the reason for that is like I said, I wanted to create this inconsistent spacing, but I wanted to make sure that none of them were overlapping. This was just sort of a brain exercise. Like, it's more complicated than it needs to be, but I wanted to just go through the exercise of doing it right and practicing precision in this script. So how does this work? Well, we could make a script that either does an array along a curve or a linear array, and then we could shuffle them around to change the location of them in the x-axis. But then you would probably have some of them overlapping. We could also just set up an algorithm to basically create random values from this point to this point, and then it would just lay them all out. It would lay a certain number of them out from that between those 2 points. But that would also most likely result in overlapping objects. So how do we avoid that? Well, basically what we're doing here is, in this section of the script, we're basically taking, let's see, how does this work? By the time I get to the end of the script, I usually forget exactly how the start of the script works. Well, basically we're creating multiple objects first. And we're creating this part of the script right here is just creating the random widths, because the width of each piece is different. So we have our minimum width and our maximum width of each piece, and then we're adding up those. We're adding up the total thickness of all of these pieces if they were smacked together without any spacing, and then we're looking at how much space is left. And that tells us how to divide that space to create the spacing between our members. Okay, and what we're doing here is, with this part of the algorithm, we've specified what the minimum spacing is and what the maximum spacing is, and that's how we avoid having any overlapping components. And then we create a random list so that we're getting random spacing. Now, it's important that we put different seed values into each random component, or else we're going to see some amount of patterning that we don't want. We want to make sure to break up that patterning. And so basically what we're doing here is we've merged these numbers, which is the thickness of our members, and then these numbers, which is the width of our spacing, right? And we've merged them, but we grafted our merge inputs so that we're getting alternating streams of data. So we're getting one stream of data from this and then one from this, because we've grafted it and then we flattened it on the output. So we're getting the width of a member, and then the width of a space, and then the width of a member, and then the width of a space. And that way we have a list of our data for how we're going to create our members and our spaces. And this is intentionally made to go beyond the total width of the wall, because we need to specify these parameters. We don't exactly know how many members we want. We can't necessarily specify how many members we want in this wall, at least in this iteration, because we're more focused on the spacing in the dimensions of these members. So I'm letting the algorithm figure out how many what the number of members we want is. So this list is actually going to go beyond. If I put all these members in, it would go much beyond this wall. So we've capped it basically. We did a mass addition, and we used the partial results output of mass addition, which adds each one sequentially, basically, right? So it's adding each value in this list is a summation of all the previous values. And so that's how we get this kind of stepping list, which tells us the step of each object. And so this is how we find our cap, because we at some point in the algorithm we go beyond our width, which is 8 meters, so it's 8,000. So right at item 77, we've gone over our maximum width. So our script is going to find that maximum, which is right here, or which is right here. Our index is 77, like we said, and then what the algorithm does is it basically accounts for the fact that the spacing may not totally conform to 8 meters. So we're doing a little bit of math here to conform to find one of the spaces that can be reduced, and we're reducing the whole installation to fit into an exactly 8 meter space. So, I'm not going to go totally in depth into all this stuff because I'm trying to make these tutorials just kind of an overview, and we can go into this. It would take a long time to really go into everything that's going on here. So I'm just kind of trying to give you an overview of the methodology. And so from that point, once we've created we know how many members we want. We fit them all into that spacing, into our maximum width, and we figured out the spaces of our members. At some point in the algorithm, we can use that data to create our base rectangles, which is down here. Okay. So we're plugging in, like, from this list of, these are our partial results from our mass addition component. From this list, that's how we can create the origin of our rectangles, and we can also create the domains of our rectangles. And that's how we get our base rectangles, as you can see down here. We can extrude it, which is the simple part. Then we can also create an XZ plane at the top of our vertical extrusions. And that's where we can make some more rectangles. And we can extrude them to create those overhead members. And we'll just cap all of those members to create our solid geometry. So we have some fancy stuff going on here that I'm not going to get into, but this part of the script is being used to locate these punches. So I've located these punches so that the edges of the frames are lining up exactly with one of the members. So these sliders are being used to identify which member I want to line up with. This wasn't something that I could automate. I couldn't think of a way to automate this because there wasn't really a direct pattern about how this worked. If there was a pattern, I would have tried to automate it, but there's not really a pattern. All I can tell is that it looks like there's a spacing of 3 vertical members between these punches. So I just kind of did it by eye, and I'm using these sliders to visually line up the punches, the frames. So all the frames line up perfectly with a vertical member, and then the algorithm basically is set up to allow 3 in the spacing and 3 on each end. So we only have to mess with a few sliders to obtain this result. And then we're creating our frames using some of that same data. And we're also splitting up, if you can notice, we're also splitting up these frames into like mitered sections. And that's just for the purpose of rendering. That's why you see this miter. And it's super important to do something like that so that your renderings look proper. Right, so you can see that miter. It looks so much better than if I didn't put that miter there. Then the wood grain would be going in the same direction, and this would be a seamless joint, and it would not look realistic. These are some of the details that really make a difference, and so I needed to make sure to miter that corner, that edge, that corner. Okay, and then some of this stuff is just basically making like the cushion, which is not that exciting. Just a lot of connections. Again, the whole thing, it's entirely parametric, so if I change the width, the whole thing will change, or the height, or I can change the size of the punches, which is why it looks so complicated. If I was doing this for a client, I would spend a lot more time cleaning this thing up. But, this is just a quick case study that I'm working on, just for the day. So I'm not going to spend time to like clean it up and make it look really neat. One thing I should point out is like a lot of time, you know, putting a fillet or a chamfer on your edges is going to make a huge difference in your renderings. And you can see that, you know, very clearly, like in this cushion, right? Putting a fillet on that edge made a huge difference in the visual effect. I didn't put fillet. I didn't do too much. You know, there's very little detail in this model, so I kind of just prioritized. But I knew that that was one of the things I had to do, is put a fillet on that edge, or else it would have looked weird. Okay, and then all this stuff. This is where we placed the lights that you can see up here. Again, it's all done in V-Ray Grasshopper, and so we have our lighting in between these slats, or in between these wood objects. And this part of the algorithm, I basically placed the lights with these curves, because again, in this case, there wasn't any pattern that I could identify in terms of placing these lights. It's kind of random, but I didn't want it to be totally random, because it kind of looks like the lights are being grouped. It's like there's one here, and then it skips one, and there's a light here. There's one light here, just two lights here. So there's not really a pattern, but they're kind of grouping. So I didn't want to make it totally random, but I didn't know what pattern to conform to, so I just laid them out kind of manually. All I'm doing with these lines is laying them out like in their approximate position, and then this part of the script finds the exact middle of the midpoint between the two objects that this line is closest to, basically. So this is like not an accurate operation, which is the goal, is just to do as little as possible manually. So I'm just placing these like roughly where they should go, and then the algorithm makes sure that they go exactly in the center. And so we're creating a light rectangle for V-Ray, and that's how we're achieving that. And this is just an overall light rectangle for the ambient light. Oh, and we're also, we created some punches at the same time that we created these frames. We created some objects to do our Boolean difference, our solid difference, right? So that's how we created that solid difference. These are our original members, and then we punched a hole in them with this member. Okay. And this is our back wall. And what we're doing over here is we're splitting up these members into separate groups for the purpose of rendering only. So everything up to here is just modeling, and then everything after this line right here is for rendering only, just for the purpose of representation. So what I've done with this is I use this part of the script. I use this in a lot of different projects where I just use it to split up the components into different branches. And I do that so that I can use slightly different colored bitmaps when I render it. So I'm basically taking all these objects, I put them through the jitter component, and it messes them all up and puts them into a totally random order. And then I split them into 6 branches based on this slider. In this case, I split them into 6 different branches. So you can see now, if you look at the sublist component, you can see that we have 6 branches coming out of this, right? And so that means that these are randomly sorted into 6 different branches. And then I'm exploding these B-reps into separate faces, because it's going to be easier to do our texture mapping if we're using separate surfaces rather than joined B-reps. And so but I'm keeping the faces in the same branch, so at least the different faces of one B-rep has the same color material applied to it, but different B-reps are going to have a slightly different color material applied to it. Okay, and the rest of this script is being used to identify the long direction of the face, so that the wood is oriented so that the long grain is oriented in the long direction of the wood. So we're measuring the UV dimensions of each surface individually. And this part of the script is basically saying if the U is longer than the V, that's good. Then that means that the bitmap is going to map it properly on the surface. But if the U is shorter than the V, then that means that the bitmap is actually going to map in 90 degrees in the wrong orientation. It's going to be 90 degrees rotated. So it's going to look weird. It's going to look unnatural, especially to those who are, trained to see these types of things. So this part of it basically is just like a filter to say, like, if U is shorter than V, then create a rotation. So we put a rotation into our V-Ray bitmap, which is where we create our material. And we're also creating a random offset. So we're offsetting each of the bitmaps on the surface to some random algorithm. And all this makes a huge difference in our rendering, because as you can see, like, these miters are a lot more distinguished. Not a lot more, but they're distinguished enough for us to pick it up, and it looks a lot more realistic. Again, this is like a rushed rendering. This is just a simple case study. Like, I'm not putting any time into this really. But I still think it makes a big difference to just make a nice, simple, realistic, like semi-realistic looking rendering. And so if you notice, like, everything's been texture mapped properly. So all the long grain is going in the long direction of every single member. But if I just didn't put this into the script, some of these members would have the long grain going in this direction as it's going down the vertical member. It looks awful, right? Texture mapping with wood, you have to be careful. Or else, if you want to do a really quick rendering with wood, just don't use anything with grain. Make it a monolithic material if you want to do a really quick rendering. Because trying to render with wood, but rushing it's gonna create a terrible result, right? And so again, the reason, just to clarify, the reason that we have these 6 different groups, these 6 different branches, is we actually have 6 different material files. Right, so we have 6 different material files that are slightly different colors, but this is all taken care of parametrically, and what we get is a little bit of a contrast between each piece, and that makes it a lot more realistic, right? So that's the basics of how this is all working. Hope that was a little bit valuable to you. Hope you enjoyed the video. If you have any specific questions, I might be able to help you. I know that, I rushed through most of the script. We didn't really cover it because, again, I'm just trying to make short videos, just going over overall concepts while I'm working on more in-depth videos at the same time. But I'm trying to just create these case studies to show you guys, but also for myself, just to go through the exercise. So if you're interested, take a look at a project like this, or maybe this one specifically, and just try to figure out how you would create a parametric model. Think about what kind of parameters would be demanded, and how you would go about solving for that requirement. I think it's just really important to do this often, to train the brain to think along these lines, to think from the perspective of data management, and from the perspective of, in a mathematical way and a geometric way. So that's why I do it. Hope you enjoyed. Hope you learned something, and I'll see you later.